And the idea is that without any mappings, then there cannot be any accesses to the memory. So I've been working on huge pages. And so guess memfd makes use of other allocators within the kernel. So when huge pages are involved, I get pages from huge TLB, and for THP, the plan is to get pages from the buddy allocator at larger sizes. And guess memfd will take ownership of this memory. So using huge TLB as an example, taking ownership means taking the memory and then unsetting the huge TLB flag, removing it from the huge TLB active list. So it's not quite a huge TLB folio after guess memfd takes ownership of it, except for HVO. So we retain huge TLB vmemory optimization because we want all the memory we can save. So guess memfd must of course support sharing for confidential purposes. So when a guest requests to share the memory, we need to look ahead to the conversion back from shared to private. So when guess memfd looks ahead by doing this splitting, we split the folios to the individual struct pages so that we can make use of the struct page ref counts to track the current users. And so if on conversion from shared to private, if there are more ref counts than we expect, and the number of ref counts that we expect are just the number of ref counts that guess memfd holds. So if there are more ref counts than we expect, then we have to disallow the conversion. So the problem here is that folio splitting is really expensive. So there's both time and memory cost here. So the time cost is in all this work that needs to be done. We split the file map entries, which involves allocations, because the X-array is what the file map is built on. So in order to split, say, from a 1 gig to 4K folios, then I have to allocate a whole bunch of nodes within the X-array tree. And then I also have to undo huge TLB vmemory optimization, because now I have to use ref counts on the separate pages. And of course, there's the actual splitting of the folios, which is mostly copying of flags from the head page to all the tail pages, which is 262, 144 pages to split to. So then there's also the memory cost in all those allocations over there. So the train of thought here is that if the folio splitting is so troublesome and expensive, why not just not restructure the folios? So I'm proposing that we see guess memfd as just managing mappings within all the different page tables and manage users of memory. And so that forms the two components of the proposal. The first part, I'll step into each of this separately. So the two components are managing mappings and managing users. So taking a closer look at guess memfd, it actually already manages mappings in many parts of the kernel. So the first is, of course, the stage 2 page tables. Guess memfd tells KVM what level to map at, like whether it's 1G or 2M. And it also tells KVM to unmap pages during truncation, for example. So if guess memfd receives the usual truncation requests from user space, then we tell KVM to unmap all those pages that got truncated. During conversions, we will also be unmapping from host page tables. On this, there's a contribution to remove pages from the kernel direct map. So there's the second mapping that we already manage. Then the third mapping is a patch series that I put up recently about that makes guess memfd support conversions. So this is the one that will remove mappings in host page tables for shared to private conversions. And there's some work in progress that I'm working on to tell CoreMM what level to map the pages at. And the last one is the one that I want to bring to this discussion, which is that currently there's some discussion on this about unmapping from IOMMU page tables on conversions. And I want to see if we are all aligned on this, having guess memfd manage the IOMMU page tables. So this was discussed in the context of confidential IO. So when confidential IO is supported for guess memfd, I believe the plan is that we will get the IO subsystem to directly get pages from guest memfd, and therefore the reverse is also true. We would then ask IOMMU to unmap. So stepping into this a little, the requirement here is that in addition to the host page tables, the IO devices must also not write to the guest private memory. So during a shared to private conversion, we unmap shared pages on conversion to private and unmap private pages on conversion to shared. And what I'm thinking for how we can implement this is that the IOMMU pages will get pages directly from guest memfd, and then in that process, it will give guest memfd a handle so that guest memfd knows that this memory is being used by the IO subsystem, and then we can tell the IO subsystem to do the unmapping. Yep.
So how will guest memfd know if the device, let's say TDISP device, has been set up to DMA directly to the private memory?
That's yeah. So I was thinking that for currently the process is that the user space address is handed to the IOMMU mapping functions, the ioctls.
Okay.
So I was thinking that we could enlighten the IOMMU that if this VMA belongs to a guest memfd inode, is related to a guest memfd inode, then talk to guest memfd to get memory, to get pages.
Yeah, but I don't know. My question is a little different, maybe, or maybe I'm not understanding. I'm saying that when it is a TDISP trusted device that can DMA to protected pages, you don't want to remove it from the IMMU page tables, right? You want to, in that case, DMA directly to the protected pages. So how will guest memfd sort of understand that?
Guest memfd knows if the page is private or shared. So depending on what direction the conversion is, then we will unmap accordingly. Unmap the other one.
No, but you realize that for TDISP devices that have been accepted into the confidential VM,
yep,
it's okay to DMA directly to the private pages.
Yep, it is.
Yeah, but how will you know that?
So those will be mapped as private.
Yeah, but you want to keep the IMMU mappings, right?
Yep.
To the private pages there.
Yes. So, well, I think I see what you mean. So, yeah. So I guess there's some additional tracking that needs to be.
Yeah.
Yeah.
Okay.
Yeah. Thanks for pointing that out.
Thanks.
One of the way we do on ARM right now is like for shared pages, as in what we do is the VFIO. I mean, we get that memory fault exit back to the VMM, and the VFIO will do the unmap. And for the private pages, CCA kind of use the stage 2 for the private translation. So we can use KVM's pre-fault ioctl to kind of insert the private pages into the stage 2, which kind of makes it available to the IOMMU by default. Ideally, yes, if guest memfd can do this, it's also good. But I think there is also an alternate path where KVM pre-fault APIs, I mean, in-place conversion won't happen, but then if you use KVM pre-fault APIs, you are actually saying that now go pre-fault a new guest private memory in the stage 2, and by virtue of it being in the stage 2, will make it available to the IOMMU. In certain architectures, at least on ARM CCA, because we kind of reuse the stage 2 for the private IOMMU.
Okay, I see. Oh, that sounds.
So there are two parts, right? One is VFIO doing the unmap for the shared mappings, and the other is which will do perfectly fine. VFIO will go and do. Like there are architectures where you could look at it as two IOMMUs, right? One secure IOMMU and one non-secure IOMMU, kind of a thing doing this. So for the secure side of the MMU or the trusted kind of thing is where guest MMFT would need to build and tear down the translations. It could also be done through the KVM ioctl called pre-fault. Is what I'm saying. I mean, at least that's what I'm currently using, pre-fault APIs.
I see. Yeah, I think that's something I'll take note of. I'm trying to work out the interactions now. Yeah. Yeah, Will.
Hi, Ackerley. Yes, I'm sorry, I'm a bit confused by this. So as I understand it, right, one of the original motivations for guess memfd was that if the CPU can be coerced into trying to access some memory that it shouldn't be accessing, some private pages, then all sorts of things can go wrong, right? You can get machine check, or all sorts of things can crash and burn. It doesn't obviously translate to the IMMU, that argument. So I don't understand why the host kernel has to make any changes to its view of the IMMU, because whatever your confidential hypervisor is going to go and isolate the DMA somehow anyway. So what's actually the problem if you leave those IMMU mappings in place from the host perspective?
Maybe I'll talk about the part that I'm more familiar with. So if it's putting confidential IO aside for a moment, if it right now, if we map it if we make it available to the host as shared, and then the IOMMU gets control of that memory, and then if we don't request force the IOMMU to unmap, then the IOMMU could be tricked. The IO device could be tricked into writing to those memory, and then everything will fall apart the same way as if the host wrote to it.
You're assuming you have a confidential hypervisor.
Yeah, you can't trust the host to do this, right? So
The host can do this voluntarily in order to protect itself from bugs, and has been doing it.
You can do this voluntarily in the host without having something enforcing it for you, right? You can voluntarily take things out of the direct map. You can voluntarily make sure that you cannot accidentally DMA to memory. All of this is very valid and has, it's been an important part of security posture for years, right? Having a confidential hypervisor to enforce it for you is yet another defense in depth, but you should absolutely be able to take these things out of all of the page tables for yourself voluntarily. It's not good enough just to say, okay,
I'm just not sure. I don't see what you gain. Sorry, Ackerley, I'm hijacking your talk. I'll be quick. But like if you take CCA, for example, the IMMU manipulation done by, say, the RMM will be sufficient to isolate DMA. So why does the host kernel have to do anything? All it's going to do is do things like end up cracking block mappings down to page. Okay, well, take PKVM is also the same. So you're saying, okay, so there are some technologies where you have to do it in the host. Okay. Okay. So as long as this isn't enforced, because I don't want to do this because it's going to be expensive. Okay.
The question I had is like how much of this has to happen in kernel space versus bouncing it via user? Like, for example, like you're trying to just basically glue these subsystems, right? You're trying to glue the effectively the VFIO subsystem with the actual guest memfd subsystem. If any page transition between shared and private would bounce via user space, then you could just as well indicate to VFIO no longer map this over here, which you can today. Don't get me wrong, like a VFIO does not have that ability. That's a big deficiency we have anyways for things like eventually VSM, right? So VSM will need that capability as well to poke holes into your own editor space after the VM is launched.
I guess for guest memfd, it's sort of a defense kind of requirement that we require the unmapping, or more maybe to more fundamentally, we must ensure that there are no users. So the direct way is to force them to unmap, and another way is we find out who's using it, and then as long as there's a user, we don't allow the conversion. So
fully understand.
bouncing,
It's just like where does this gluing happen? Do you do that from your user space orchestration, or do you do it from in kernel? I'm fine with either, but user space definitely will have to have a say, especially when we get to things like planes and VSM later on. User space will have to have the ability to say, hey, I know I told you at this offset you could do IO DMA, but now you can no longer do that, please, because my BTL protection changed, right?
Yeah, so user space will continue to have its.
Doesn't have it today.
It doesn't have it today.
It doesn't have it today. Wait, Mike.
The other way to ask is what will be the user space API for mapping and unmapping guest memfd pages from IMMU. Like right now, we have like IMMFD, DMM app, or VFIO, DMM app kind of a thing. What will be the one that will be driving this from the VMM or from the user space?
Impression that one of the IOMMU ioctals, there exists an unmapping ioctal already. So
I think in the case where we do have a confidential hypervisor, it needs to essentially redirect to that backend instead of manipulating its own page tables. Or at least in the case where we have a confidential hypervisor and the extra layer of page tables, the stage 2 that can protect you. You can imagine a hypervisor running on older hardware that basically just has strong opinions about how the page tables are set up. Oh God, I'm imagining Zen now. But you can imagine a case where you still do have to take it out of your own page tables or ask the hypervisor to, even then. But yeah, we need to redirect these requests to the correct backend, either the hypervisor that can do it for you or just voluntarily take it out of your page tables.
thanks. I'll follow up with on this.
I guess conversion between private and shared memory needs guest cooperation.
Yeah, it does need.
And what if the guest is a malicious one and does not do such cooperation, and this guest just DMA into its private memory, and this GPA range just still kept mapped on the LMMU? It will just crash the host.
Yeah,
right?
so that's the part that I'm hoping to directly do the unmapping. So
Yeah, so I mean, you can unmap the parameter memory in the host page table so that the host CPU will not read or write into this private memory so that there will be no machine check on the host side. But malicious guest can initiate DMA into its private memory, causing machine check on the host. So it's a choice of a guest to not cooperate. So how do we solve this?
So
what kind of testing do we? Yeah.
So there's a kind of a mechanism like attestation to make sure the valid guess will be run by the confidential computer. So that will make sure no malicious guess.
we
There are people online. I mean, even the device. So we are not talking about TDs, right? So we are actually talking. There could be some untrusted devices sent to the VM. Yeah.
To pass this to David here, but I don't think an untrusted device can DMA into guest private memory. No, right?
I don't think it's.
No, like it depends on your underlying architecture. But like if that would be possible, your hypervisor already breaks all the confidentiality guarantees you want. For ICP-SMP, I know for a fact because I tried. I mean, not maliciously. I just tried to see what actually happens. Writes don't work. They just get blocked. Reads succeed, so you see the ciphertext.
So yeah, but how does the MMU block the writes? Yeah.
I mean, our hardware checks it as part of the confidential compute architecture. So in the AMD design, if the write's not allowed, it's just blocked. Other architectures work differently. like TDX. But in the AMD one, I don't think this is really relevant because there's no risk.
Yeah, like David said, this is a TDX specific problem. And we pointed out ARM CCA uses GPT checks to prevent the writes. SNP uses RMP checks to prevent the writes. TDX has no protection against the writes. And you're absolutely correct. There is no way a host can inspect the operation of the guest to know whether the guest is going to attempt DMA to a page that would cause a machine check. The only way the host can keep itself safe is to do exactly what is being described here on TDX. TDX mode.
Well, so yes, you can screw yourself over and make the machine crash if you DMA to a TDX page and write to it. Yes, that happens. But it's not protected against. I didn't build it. But I mean, it's a straight write, right? Essentially, nobody should be writing to it. If you do, you're dead. Right now.
Well, but the problem is on TDX, as we pointed out, the guest can target anything in its address space. It could target a private page and telling the device that it's a shared page. And on the TDX architecture, that will cause a host level RAS problem.
You need to use that. The audience can. Just throw it.
You want it, James?
Yeah, I'll catch.
So where was I? So I mean, it does sound like a TDX problem. It's not protected against. The VMM can already do this in a lot of different ways. Yeah, and I don't know if, I don't know what happens if a guest actually tries to do it. It sounds like it might get screwed up, but I don't know. I believe you if it did. So.
It is a machine check and the host crashes, which is probably not the behavior you want on a misbehaving guest, is to take down the entire system. Clouds tend not to like it when a guest can crash the whole host.
Yes, we should not let the guest crash the host. Yes, full stop.
Yeah, so that was precisely why guest memfd was like set up to do this, to orchestrate this stuff. Yeah, and then I hope that answers the question on like forcing the IOMMU to unmap.
Okay, fine, but then coming back to the TDIS point, you can't do this anymore when you have TDIS, right? So,
So
what value is this?
I'll think about that a bit more.
Okay.
Yeah, but I guess for TDIS, there'll be some additional tracking to decide what needs to be unmapped and what doesn't.
On TDX, I mean, even with TDISP, there are separate IMMU page tables for the private and the shared GPA space. The private GPA space is managed entirely by the TDX module. Shared GPA space is whatever the host wants it to be. So at the time of a page conversion, the host can do the IMMU splitting like this. If the guest attempts it with the wrong polarity, if it's a true TDISP access, it's got to be in the security PT. If it's not there, TDX module protects you. If the guest is trying to do it the wrong way, using shared semantics on a private page, you want the host protections to be in place so you can stop the machine check.
With the last 3 minutes, I'm going to say that I think this is managing mappings is still insufficient because there are other users of guest memfd, and the remaining users are the significant remaining users are those that use GUP on guest memfd memory. So I'll jump ahead a little bit. The plan for this is I want to see what everybody thinks of exposing guest memfd memory as PFN map VMAs because PFN map doesn't allow GUP. So basically, we are managing the users by telling everybody who uses GUP to not use guest memfd. And does it sound like, at least for Coco, does it sound like there's a significant number of setups that would benefit from this? Like, is there a significant number that can avoid using GUP? So suppose virtualization is offloaded to the IOMMU, and the IOMMU has its own way of accessing guest memfd already. or
One thing that we found is with shared pages, GUP's not that interesting anyway, because when the pages get passed to some driver to do DMA and it ends up bouncing anyway, because if I recall correctly, the DMA APIs aren't aware that the pages are shared, and so they think they have to bounce anyway. So you can kind of work around this in the VMM by, I mean, if you're going to have to bounce anyway, we could fix that in the kernel. But if you have to bounce anyway, you might as well bounce into VMM local pages, anonymous pages or whatever, and so yeah, then you don't need GUP. So that worked out okay for us in OpenHCL, which is kind of a VMM in a very specialized environment. So maybe, I don't know. In at least some cases, it seems reasonable.
okay. Yeah. Thank you. I'm out of time. Please do feel free to reach out about anything about Guest memfd. Thank you.